a work, continuation of the work that we presented last year. This is the continuation of work that Luca presented last year. And so let's get into the topic. So we want to simulate rotors, the fluid dynamics of the rotors, but rotors are getting more and more flexible. For instance, we have here wind turbines, and with the current blade radius growing bigger than 100 meters, we cannot neglect anymore the flexibility of the blades. And another example that we have here on the right is that of a helicopter rotor. So we have not only the flexibility of the blade itself, but also we have a few hinges that cause a change in the kinematics of the blade that we need to put into our CFD simulations so that the fluid solver gets this information and we can get to more accurate solutions. So the framework we are proposing is a partitioned approach. So we have two separate solvers. As a flow solver, we have SU2, whereas as a structured solver, we use MBDyn, which models, let's say, the flexibility with beams. So it's a low-order modeling of the structural problem. And those are coupled with the coupling library PreCICE that we have seen before with another work in another presentation. And today I will talk about this beam to surface mapping, so mapping data from one-dimensional beams in MBDyn to the surface in aerodynamic surfaces in SU2. And also we will show that you can use the structural solver to set the blade kinematics in the SU2 simulations. So I will give a brief presentation about the codes and an overview of what we have seen at last year's presentation, show the new layer that we use for data mapping from the 1D problem to the 3D problem, a two-dimensional test case, a three-dimensional test case, and a small application on a helicopter rotor. So the framework is shown here on the left. So we have PreCICE, which is this coupling library. We have a C++ adapter in SU2, and we have a Python adapter in MBDyn. And what does PreCICE is to map the displacement from one solver to the other, and the forces from the fluid solver to the structural solver. Here, it's important to mention that these are displacement and not rotations. And these are forces and not moments. And this will generate a problem in the mapping. And regarding PreCICE, it has some notable features. We can set different time steps between the two solvers. We have implicit and explicit coupling. The implicit has also some acceleration techniques built in. It already provides data mapping with using, for instance, radial basis functions or their nearest projection. And these mappings can be either conservative or consistent. So we use conservative mapping for forces so that we preserve the integral value between the two domains, and consistent mapping for the displacement. Regarding MBDyn is a multi-body code, so we can describe the kinematics of some arbitrary mechanisms, and this gets translated into equations of motions that get solved. And here at the bottom, we can see a very simple example of how it can work. We have some nodes that can represent these different things. For instance, here we have a node with a hinge, and then we have other nodes which together can form a beam element. So nodes can be linked together in a rigid way or in a flexible way. In this case, we are using this non-linear second-order finite element-like beams. And each node has 6 degrees of freedom. So we have 3 degrees of freedom for the displacement and 3 for the rotations. And the code has widespread use for helicopters, for tilt rotors, and also other let's say, domains, like also for cars, suspensions. It's really flexible, and it also includes the controls of systems. And it has his own aerodynamic solver, which is a low-order aerodynamic solver, but it has already been coupled with other fluid dynamics code. So, for instance, with OpenFOAM, with the mid-fidelity solver that we developed at Polini, which is called Dust, and we will show an example of that later. So, where were we last year? Luca presented the results from two-dimensional test case. This is called the vertical flat test case that is available on PreCICE website. and this is a horizontal flap test case. This is more involved with respect to the fluid dynamics because we have vortex shedding that is exciting the response of the structure, whereas this is more of a verification test case. And so we have shown a problem that is, since we have like our beam and we have the nodes which store the displacement and the rotations, if we simply map the solution in this way, we can also have a map to the displacement, whereas the rotation is not transferred to the other solver. And so in general, we want to see how to apply correctly the boundary conditions of the FSI problem. So how to transfer the rotations to the fluid mesh, and then how to get from the local forces on the surface of the fluid mesh to forces and torques onto the structural node. So the solution is provided here. What we do is we enrich our structural model, adding a new layer of nodes. So if we have our beam, we for each structural node, we have a slice of our mesh, and we add these, we call them dummy nodes. So these are nodes that have no mass and no inertia related to them, but they are rigidly linked to our structural node of the beam. So in this way, we have that the rotations can be communicated between the fluid, the structural solver to the fluid solver, and as well the forces can get translated automatically in MBDyn into torques and forces onto our node. And in this way, we also maintain the rigidity of our section, whereas we avoid the warping of our sections. So we see here the first test case is this vertical flap in a horizontal flow field. So the structural model is made of both the structural node and the dummy nodes. So the body, which is the one we simulate in the flow field, is the one in green. The structural discretization is made of these beams that is represented by this black vertical line. And then we take from the fluid mesh, we take some slices, and in the intersection we add these dummy nodes that maintain the rigidity of our. We see here the solution from MBDyn nodes and how this gets mapped to the fluid solution. And so what we did in this test case is to take the grid, the config file, and the restart file that are provided in MBDyn in PreCICE website, whereas we have built our own MBDyn model. And here we see the solution of the horizontal displacement of the tip of our body. And so the dashed line is our reference solution, which is provided on the PreCICE website, which is made of the coupling between SU2 and calculix, which is a finite element solver. And then we see with the blue line the solution that we got without these rigid sections added, and in red we have the new solution. What is not noticeable here is that the frequency now is captured correctly, whereas before we had this lower frequency response. For the three-dimensional test case, we see the flutter of a wing. In this case, we are using the very same MBDyn model. So the structural model is the same, and we are changing the fluid solver. So it's the opposite, the other way around with before. So in this case, the fluid solver is this mid-fidelity solver called the DAS, which is coupled to MBDyn using PreCICE in a similar manner, but not the very same one, because in this case, the mapping from the beam to the aerodynamic surface is internal within DAS, and it's not made in MBDyn. So the only difference in the MBDyn model is that we have these additional nodes, whereas the structural model of the beam is exactly the same. And in DAS, the solution is provided both the discretization, and the solution is provided both with a panel method and a vortex lattice. So here maybe there is an animation, maybe not, I'm not sure. Let's see. Probably not, but never mind. So it was just an animation of this wing going into flutter, but we can see. Let's see. Oops, it disappeared right now. So Okay, never mind, no problem. We can see the plots here. They were backup. So we have the edgewise displacement. So this is the displacement of the tip in the chordwise direction that has its own frequency. And this is non-dimensionalized with respect to the blade span. And then we have the flapwise displacement. So it's normal with respect to the string and the rotation of the tip. And so we see that the chordwise displacement has its own frequency, whereas the flapwise and the torsional displacement coincide, as it should be in a flat test case, and it's very similar between the two shoulders. Last time we show a very simple test case of a helicopter rotor. So the hard to helicopter, we structural model of this helicopter, but we reduce the number of blades from 4 to 2. And in this case, we treat independently the rotation of the blade in SU2 and in MBDyn, so they are separate. And we have the rigid rotation of the body. And we build our CFD mesh on a, let's say, a flat rotor disc. And then we use MBDyn to set the cone angle of the blades and also the pitch angle of the blade. In this way, we can also set the controls of the blade during a simulation, for instance, of a forward. Here we have the results of the overstimulation. In this case, I didn't use any ramping, so the loads of the very first time step of the fluid solution is transferred directly to the structural solver, and this created this very long transient. So we can see here the vertical displacement of the tip as a function of the number of the revolutions, and this gets dumped after about 15 revolutions. Whereas if we add some damping on the if we add some ramping to the loads, so for instance, the loads vary linearly from during the first revolution from 0 to the actual value. This transitory of the response lasts about 5 revolutions instead of 15. So, as a conclusion, we have shown that there is a simple way to map the 1D structural problem to 3D domain surfaces, and the framework is able to capture both complex fluid structure interaction problems and also to set the kinematics of the blades. And what do we still have to do? Complete the automatization of the insertion of the dummy nodes within the structural model, add multi-zone capabilities so that we can have a rigid rotation of our rotor and study forward flight with a proper mesh with a weight that is meaningful and with a small number of elements, and then do some comparison with clinical data. So thank you for your attention and keep it.